Hello and welcome to PT and Nutrition Education's e-learning platform. Today is part 3 of the nutrition lecture series, and as you can see we will be focusing on the topic of dietary fat. Of course, we will be preparing you for your examination in nutrition for personal training, but we're also going to be looking at some of the myths which surround fat and hopefully dispelling some of the misnomers regards to dietary fat and whether or not it is actually the dietary villain that we all have thought at one point in time that it is. So when we say the word fat, generally we think of two things. The first one, we can think of dietary fat in the context of energy and other roles and functions that it plays within the body, but as well it has some negative connotations with regards to adipose tissue. So that's stored fat that can be around our organs, which is known as visceral fat, but also underneath our skin, which is called subcutaneous fat. So really what we want to do is trying to distinguish between the two types, and because of the negative connotations that have been mentioned with the word fat, it is very common now for people to think of somebody that might be overweight or obese and is often considered as an insult. So why is it that that sentiment has actually come around, and how is it that we've somehow villainized dietary fat and something that we should be scared of? So if we look at the headlines which have been surrounding dietary fat, there is this early sentiment that dietary fat was the villain and we should be eating alternatives like margarine, we should be eating low-fat foods or low-fat alternatives, and we should be eating breakfasts that are high in sugar, because whole grain cereals can keep you slim and fit. And also, you may remember, even back as early as 2012, there were a lot of reports talking about how egg yolks are as bad as smoking, that they can cause heart disease, all kinds of crazy headlines which were really not that long ago. And then we compare that to the most recent sentiments with regarding dietary fat, and you can see now there is a complete shift in the attitude towards eating fat. So you can see from the same paper there, instead of eating whole grain cereals for breakfast, we should be eating more fat. We should be eating more fat to stay healthy. We should be trying to cut our sugar intake. Eating full fat foods can actually reduce the chance of obesity. And then we've got these now that are saying that the likes of milk and butter are safe, but low fat versions like margarine can have a deleterious effect. So as you can see, there is this dichotomy between fat, and it has been villainized, but then it's had a resurgence in recent years. So what we're going to do is try to dispel some of these myths and look at some of the cold hard facts with regards to dietary fat, but then also looking at, like we've done for the last two lecture slides, is look at the impact on sports performance or exercise performance. So let's start with some of the facts with regards to the role and function of dietary fat. And like we said in the protein lecture, we mentioned that pretty much every single cell in your body is either a protein or is governed by the action of protein. And every single cell that we have is surrounded by a layer of fat. So we have what's called a plasma membrane, which is permeable so that particles can gain access to and from different types of cells around the body. And that is essentially a layer of fat which wouldn't be available without the intake or ingestion of dietary fat. Dietary fat also provides the backbone or production of sex hormones within the body. And also, in terms of sports performance or exercise performance, it provides the largest and primary energy source in the human body. So the muscle, the liver, and adipose tissue are places where fat can be stored and then can be drawn upon when required. So both from a health standpoint and an exercise and performance standpoint, it's quite clear that fat is certainly an essential macronutrient that we should be ingesting on a daily basis in order to carry out some of these processes outlined. With regards to exercise and sports performance, really what we're thinking of when we are ingesting fat is its use as an energy source. And this can be utilized in different tissues around the body, but primarily we are talking about utilization from the liver and also in skeletal muscle. Now, we have over 30,000 kilocalories worth of stored fat in the human body, and even somebody that is very lean can draw upon this massive reservoir of energy that we have, and then we can store that in a number of different places. Once again, we can store it in the liver, we can store it in the muscle, which is what's known as an intramuscular triglyceride, and then we can also, of course, and the one that you're probably most aware of, is storing it in a fat cell, which is also known as our adipose tissue. And maybe one of the reasons why dietary fat has been given this villainized tag is because out of all of the macronutrients, 1 gram equals 9 kilocalories. So it is the most energy dense macronutrient that we can ingest. But that doesn't necessarily mean that that is a bad thing. So when we're talking about examples of fat, the first thing that we need to distinguish is there are different classifications of lipids. Lipids is another name for fat. And those 3 classifications are as follows. We have simple lipids, compound lipids, and derived lipids. Now, as a sports scientist or gym instructor, what we are mainly interested in when it comes to nutrition from an energy perspective are simple lipids. What we're referring to there are things like saturated and unsaturated fats, which you may have heard of. However, when we talk about compound lipids, we're talking about things which are known as cholesterol, so high density and low density lipoproteins. And then also the third classification of lipid, which is known as a derived lipid, or sometimes we can refer to them as steroids, such as testosterone and estrogen. But in the context of dietary fat, what we're going to be focusing on mainly are food examples which we can put into the category of saturated fat or unsaturated fat. Okay, and then we've got further classification of unsaturated fat, which are known as monounsaturated fats and polyunsaturated fats. Now, when it comes to understanding the difference between the two, without getting too scientific, we can see that a saturated fat, okay, has a carbon backbone, okay, and these single lines here demonstrate single bonds which hydrogen atoms are attached to. Now, as you can see, every single carbon atom has a hydrogen atom attached to it, okay, and therefore that is why it is known as a saturated fat. However, unsaturated fats, okay, as you can see, some of those hydrogens are missing, okay, and they have also what's known as a double bond. So rather than each one of these connections being a single bond, you can see here that the backbone slightly curves a little bit, and this is a double bond, and as you can see, some of the hydrogen atoms are missing, and this is why it's known as an unsaturated fat. But for the context of the examination, what you need to be aware of are some of the food examples which exist and being able to name them for both saturated and unsaturated fat sources. When we're talking about examples of saturated fat, generally we can say that these are from animal sources, and also they are solid at room temperature. So cheese, eggs, meat, particularly red meat and the fat from that, are great food examples of saturated fat. When it comes to unsaturated fat, we've got 2 examples of that type of unsaturated fat, and that's a monounsaturated fat and a polyunsaturated fat. So for monounsaturated fat sources, generally what we're talking about here is the likes of nuts and seeds, such as almonds. We've got peanut butter there, olives and olive oil, avocado, which can all be put under the heading of monounsaturated fats. And then we've got polyunsaturated fats, such as fish and dairy. Okay, so if we are quizzed on certain examples of different types of fat, those are some examples that you can certainly put forward in your examination. Now, one particular type of fat that we've not mentioned yet, and really the one that should receive the negative press, is trans fats. Now, trans fats are actually genetically modified and they are processed in order to bring about a much better taste and also to increase shelf life, which therefore increases profitability of any of the companies which are actually selling these. So if there is one type of fat which should be vilified, it is definitely the trans fat. More often than not as well, they are piled full of sugar as well, so we get a huge insulin release at the same time as fat that enters into the bloodstream, and the likelihood of it ending up as adipose tissue is certainly increased, especially when we consider that eating these types of foods certainly don't coincide with an exercise session anytime soon. So the type of fat which should be looked at as the villain is definitely a trans fat, whereas in previous years the likes of saturated fat has been vilified, as you saw from the headlines earlier on in the lecture, but certainly isn't one that we should be looking at as the villain. So there we have it, all of the different types of fats with the outstanding food examples that you could potentially give in your exam. So now we're going to move on to the metabolism of lipids. So how is it that the body actually breaks down and uses fat for energy? Now, people often refer to using fat as a fuel in terms of burning fat, and that concept does have some truth to it. However, one thing that you need to be aware of is that using fat as a fuel is actually a two-step process, and those two steps which exist are known as lipolysis and then beta oxidation. So what this is in terms of breaking fat down is actually breaking up what's known as a triglyceride. Okay, now a triglyceride is called a triglyceride because it is a glycerol molecule which is attached to 3 individual fatty acids, and what we have to do is we have to be able to release these fatty acids so that they can be used as an energy source. Breaking this down in terms of the triglyceride and liberating the fatty acids into the bloodstream is a process known as lipolysis. However, lipolysis does not mean fat burning is taking place. We may be breaking fat down and releasing it into the bloodstream, however it may not actually be taken into the mitochondria to undergo what's known as beta oxidation, which people often refer to as fat burning. Now, what we have to be aware of is that with anything that is broken down in the body, of course, we need an enzyme to actually do that. Now, we have 3 individual enzymes which break down each one of these fatty acids. So the enzyme which breaks down fatty acid 1 is actually known as adipose triglyceride lipase. The second one, which is actually the most common, is known as hormone sensitive lipase. And then the third one, which is known as MGL, which is short for monoacylglycerol lipase, breaks down the third and final of the fatty acids within a triglyceride. So it's those enzymes which are actually responsible for breaking down those individual fatty acids. Now, lipolysis actually takes place in 2 different places. Of course, in adipose tissue where the fat is stored, and also, as mentioned earlier, we can actually break down fat within the muscle. So we've got the ability to store intramuscular triglycerides, and we can actually break that down within the muscle and take it straight into the mitochondria for ease of access. Now, when we're talking about lipolysis, it occurs in 2 very particular circumstances. So when we haven't eaten for around 6 to 8 hours, or of course in a fasted state, then we are likely to be breaking down adipose tissue and breaking down triglycerides in order to give certain cells around the body the energy that they need. But also, of course, when we start to exercise, we create a demand for fuel, and therefore there is an increase in lipolysis. Now, the reason for this actually occurring is that we have a hormone known as insulin, which is released when we eat carbohydrates. And when we are in a low insulin environment, i.e. in a low carbohydrate environment, our ability to actually break down more fat increases, and this is because there is a low insulin state within the body. When we eat carbohydrates, we actually blunt lipolysis for up to 2 to 3 hours, particularly after a carbohydrate feed. Another hormone which plays a part are catecholamines, which are things like adrenaline. So if we increase the output of adrenaline from the adrenal glands, then we increase our ability to actually break down and start to use those fatty acids. Now, once we've liberated those fatty acids, assuming that we've broken these fatty acids down from an adipocyte, then what will happen is that they will enter into the bloodstream. Now, glycerol, as we mentioned before, is soluble and can actually go straight to the liver by itself and can start to contribute to processes mentioned in the carbohydrate lecture, such as gluconeogenesis. Whereas the fatty acids, they need a transporter in order to carry it where it needs to go, specifically to the muscle. Now, we have a protein within the blood which is known as albumin, okay, and it can carry fatty acids to the working muscle. So much like hemoglobin carries oxygen, albumin is the transporter for fatty acids to the muscle. Now, when it arrives at the muscle, we have to cross what's known as the plasma membrane. So these fatty acids can't just enter into the muscle on their own. We actually need a group of transporters in order for fat to be taken into the muscle cell. Now, those transporters are known as CD36, FABP and FATT. Okay, now of course those are acronyms. The CD36 is what's known as fatty acid translocase. FABP stands for fatty acid binding protein, and FATP stands for fatty acid transport protein. So these are simply just the transporters, or the bouncers if you like, which will actually escort those fatty acids into the muscle. Now, once they arrive at the muscle, of course, in order to undergo beta oxidation, which means that fat is then going to interact with oxygen and then we're going to produce ATP, then what needs to happen then is that we need those fatty acids to be taken into those particular parts of the mitochondria. But just before going into that, one thing that I feel is important is mentioning that the transporters that we've just talked about have actually got the ability to increase or decrease their numbers. So endurance athletes that take part in long steady state exercise over greater durations can actually start to increase the amount of fatty acid transporters they have. And likewise, with a high fat, low carbohydrate diet, we can also increase the amount of fatty acid transporters, which subsequently increases the amount of fatty acids which can enter into the muscle cell, and therefore our ability to burn more fat may be enhanced. Now, when it comes to transport into the mitochondria, we have what's known as the carnitine shuttle. Now, the carnitine shuttle is, as the name suggests, is where the fatty acids will bind to carnitine, and what that will then do is take it into the mitochondria for beta oxidation to occur and therefore ATP to be produced. Now, you may have heard of carnitine because it can be used as a supplement, and therefore the thinking with the supplement is that we increase the amount of carnitine that we have and therefore can potentially increase the amount of beta oxidation and fatty acids that enter into the mitochondria. However, the jury is still out on that particular supplement, and I'm certainly not going to recommend that supplementing with L-carnitine will enhance fat burning. That still is yet to be proved for 100%. Now, once this fatty acid has been taken into the mitochondria, it enters into the mitochondrial matrix and also the cristae of the mitochondria, and then what will happen then, it combines with oxygen, it is oxidized, it produces ATP, and then the byproducts of that will be carbon dioxide and water. But of course you can refer to your anatomy and physiology lectures on the energy systems to gain a little bit more knowledge with regards to that. The end point, of course, is then burning fat, or in scientific terms known as beta oxidation. So that's the process of the metabolism of lipids. Just be wary that it is a two-step process, which is lipolysis, so the breakdown of the triglyceride, and then of course beta oxidation within the mitochondria. So now that we've spoken about the process of fat oxidation, we might as well talk about some of the factors which affect fat oxidation during exercise. So as you can see from this schematic, which a scientist called Rutt actually produced, and you can see that there are certain factors which increase the amount of fat oxidation which takes place during exercise, and also there are factors which decrease it. Now, as we've spoken about before in the carbohydrate lecture, when we are exercising at higher exercise intensities, then propensity to burn carbohydrate as fuel increases, and a reduction in fat oxidation happens as well. However, with endurance training, so that is over long periods of time, then the likelihood is that fat oxidation will increase. So with an increase in the duration of the exercise, the propensity to burn fat as fuel increases. Now, one thing it's also important to mention is that when we are fueling exercise, we're fueling exercise from two key fuels, and that's carbohydrate and fat. So it is extremely rare that we would be burning 100% carbohydrate or 100% fat. We're always going to be what's referred to as dual fueling. So we're always going to be burning carbohydrate, we're always going to be burning fat. However, it's the predominant energy source which can be determined by things like the duration of the exercise. As I've just mentioned as well, the intensity of the exercise can play a part in whether it increases or decreases fat oxidation. So as we've mentioned, the higher the intensity of the exercise, then the reduced amount of fat oxidation that takes place, whereas in a moderate or lower exercise intensity, then the increase in fat oxidation is what will occur. There are certain circumstances as well which can decrease the amount of fat oxidation, and one that we've spoken about at length now, especially in the carbohydrate lecture, was introducing carbohydrate into the diet, especially before an exercise bout or an exercise training session. So the reason for that physiologically is that carbohydrates bring about a response in the pancreas to release insulin, and when insulin is high within the bloodstream, then there is a blunting of lipolysis and a blunting of fat oxidation. So carbohydrate prior to training will shift the body to actually use that carbohydrate for fuel during exercise. Okay, now the jury's still out on the remaining two in terms of the mechanisms behind it, but it has also been found that hot environment or at altitude can actually reduce fat oxidation. However, they are still elucidating why that actually might be mechanistically, so I certainly don't want to have to comment on that at this moment in time. So just know that there are certain instances which can increase fat oxidation, and there are certain instances which can decrease fat oxidation. So alongside the factors which affect maximal fat oxidation, we have what's known as fat max. So this is an exercise intensity with an individual which will burn the most amount of fat during an exercise training session. Now, there may be a fat burning zone, which a lot of people have heard of, and the fat burning zone is more often than not identified at a certain treadmill speed in your public gym, for example. Now, one thing to dispel from this is that the common fat burning zone, which you might be set at on a exercise treadmill, and the speed which they set for you, doesn't necessarily mean that that's the best fat burning zone for you. Now, of course, as we've just mentioned, at lower exercise or moderate exercise intensities, we have a propensity to burn more fat. However, what's really hard to determine is that every individual has a different maximal fat oxidation rate. So this is the exercise intensity, which is measured by our percentage heart rate max, which increases the most amount of fat oxidation during an exercise training session. Now, having looked at many different studies which look at the whole spectrum of fat max, and there has been a lot of different data with individuals across the whole spectrum of athletes and recreational athletes and so on, and it's been found that fat max can really differ between 50-75%, and even in some individuals up to 80% of their maximum heart rate, where they are burning the most amount of fat. So that's determined, as you can see by this part of the graph here, in grams per minute. So the amount of grams per minute of fat that they're burning based on the exercise intensity which they're actually training at. Now, what's also hard to gauge from this is that we might get somebody on the treadmill and they may have the most expensive equipment in the world to find out what their fat max is, and we can say that at 65% of somebody's heart rate max for this individual is when they're going to burn the most fat. So we set them off on a training program where we exercise them at 65% for longer durations, as mentioned before, and we may get a superior fat oxidation rate. However, we may get them to do this over the course of, let's say, a 12-week period, and what will have happened is they would have got fitter, their VO2 max will have shifted, and therefore their percentage heart rate max, which they have to work at 12 weeks down the line, may not, once we get them back into the lab and get them tested, may not actually be conducive to the 65% that we originally set, because that fat max will have shifted based on their VO2 max shifting and based on their percentage heart rate max shifting. So this really does present an issue by saying that individuals should train at a certain intensity to bring about the most fat oxidation rates, because it is a sliding scale and it does change based on the individual and based on that individual's fitness as well. Now, a lecture on fat wouldn't be complete without one of the hot topics in sports science at the moment, and that's the topic of fasted training. So fasted training is simply exercising without any food or energy drink prior to that exercise session commencing. So water or black coffee, more often than not within the field, is still seen as fasted training. And the reason behind fasted training being so popular is the theory that it can help increase the amount of fat that we burn during and also after that exercise training session has taken place when in a fasted state. So I just want to draw your attention towards two scientific studies which pose that very question. The first one, which is a research article from the authors, as you can see here, and the topic of the article is, of course, the 24-hour fat oxidation rate when training in a fasted state. And what they wanted to do was they wanted to compare to see whether that is superior versus training in a fed state. So what happened here is that they gathered 10 recreationally active lean males and they worked them at 50% of their VO2 max for a 60-minute duration. And as you can see from the results, the exercise which took place after feeding at lunch had a lipid oxidation about 446 kilocalories per day. Exercise training after dinner, so later on in the evening, had a slightly less lipid oxidation rate at 432, with a standard deviation of 44 across the 10 individuals. But as you can see, the fasted training group nearly doubled the amount of lipid oxidation when training in a fasted state before actual feeding. Okay, so one of the takeaways from this may be that fasted training does in fact increase the amount of lipid that is oxidized during that exercise training session. Now, like with all scientific study, you should have an open mind, and you should certainly be questioning certain aspects of the paper. And one thing that you should be questioning about this paper is that when reading the full paper, they did not elucidate the full amount of calories that was burned from other fuels. So for example, in the fed exercise training session, although there was less lipid actually oxidized, that may have been down to the fact that more carbohydrate was oxidized. So therefore the amount of calories that were burned over the course of that 24-hour period may have been equal to, or if not more, than the exercise in a fasted state. Not saying that was the case, but that's certainly something that you could be questioning with regards to these different exercise protocols. However, one key takeaway, of course, is that the amount of lipid that was utilized during that exercise training session and for the rest of the day was nearly doubled in a fasted state. In addition to that study, we've also got this research study which looked at not only the amounts of fat oxidation which took place in a fasted state, but also the amount of energy intake which then followed after a fasted training session. And it was really interesting to see that those training in a fasted state actually reduced the amount of calories that they were eating over the course of that 24-hour period after that exercise session had taken place. Now, the individuals were allowed to eat ad libitum, which means that they can eat as they please, and just from simply training in an exercise fasted state, that they actually reduced the amount of calories that they were eating, and therefore it may have had a appetite suppressing effect. Now, when you consider you've got clients which may want to embark upon a weight loss effort, then this is certainly a strategy that could be useful to reduce appetite and therefore increase the amount of weight loss or fat loss, depending on your macronutrient prescription, which actually occurs. So not only did it show to increase the amount of lipid oxidation during exercise in a fasted state versus a fed state, but it also reduced the amount of calories that was ingested over a 24-hour period. So there's certainly some takeaways there in favour of fasted training that you may want to implement depending on the goals that your client wants to achieve.